Then in the green code on the bottom of slide 6, I'm defining lam3 as a lambda. This lambda returns a value. Specifically, it returns the sum of its two int arguments. And since I have not specified a return type, the compiler deduces that this thing must be returning an int. Consequently, in this cout statement, when I call the lambda whose name is lam3 with the arguments 4 and 7, that computes and returns an int 11, and I see that int 11 in my output. Then continuing on to slide 7's code, the bottom half of this little program. This time I'm defining a lambda and I'm specifying that this lambda returns a double. Now in this case, I don't have a choice about whether I specify the return type. I have to specify the return type because notice that this lambda definition has two returns. In the first return, in the case where the parameter i's value is greater than the parameter j's value, I'm returning I, which is an int. But if I is not greater than j, I'm returning j times 0.125, which is a double. So here I have a situation where the compiler does not have a basis for deciding what the return type is supposed to be, and I have to tell the compiler, in order for this to work, that this lambda will be returning a double. When I call this lam4 with the arguments 4 and 7, well, i's value is 4, j's value is 7. Since i's value is not greater than j's, I'm going to return 7 times 0.125. That is, I'm returning 7/8, which is 0.875 when that's displayed on the screen. And one more example, this time using some standard functions within the body of the lambda. This lambda, which I'm naming lam5, takes a double as its argument, and it's using some standard functions, cosine, square root, and exponent, so that we get the cosine of the square root of e to the x as our result. When I call lam5 of 2.5, all right, I'll confess that I cannot do this calculation in my head, but what we get out on the screen is minus 0.9398, which certainly makes sense as the cosine of something. Okay, so that's some examples of defining and naming and calling lambdas, some of which take arguments and some of which return values. Now, at the point where you define a lambda, it's very likely that there are some other variables in the same scope where you have defined that lambda. For example, if you've got a function and you define a lambda within the body of that function, then that function may have parameter variables, may have other local variables that are in the same scope as the lambda. Now the lambda can capture, that is, gain access to either values or references to these other objects that are in the same scope as the lambda. And you do this by using various notations in the square brackets that denote the lambda introducer. For example, if you put an equal sign inside the square brackets, that means that within the body of the lambda, you would like to be able to have direct access to the values of all of the other objects that are in scope at that point where you have defined your lambda function. On the other hand, if you use an ampersand in the square brackets, that means that you would like to be able to capture all of the objects that are in scope by reference rather than by value. As opposed to capturing all of the objects in scope either by value or by reference, you can constrain which object or objects you want access to by just naming that particular object. So for example, if there is some object J within the scope where you're defining your lambda, you can give J within the lambda introducer to indicate that within the body of the lambda you just want to be able to use the value of j. On the other hand, if there's some y object in the scope where you have defined your lambda, then you can access the y object by reference within the body of the lambda if you say ampersand y in the introducer. And you can sort of mix and match what's going on here. For example, this notation here, j comma ampersand y, means that within the body of this lambda I want to be able to access j by value, that is, I want to be able to read from it but not modify it. But I want to be able to access the object y by reference. I want to be able to both read and modify y. If I use, on the other hand, an equal sign in the square brackets, that means that I want to be able to access all of the objects in scope by value. But here, by also saying ampersand y, I'm saying, by the way, I want to access the value y by reference. Okay? So within the body of this lambda, I will be able to access all of the objects that are in scope at the point where I have defined this lambda. Almost all of these I will be accessing by value, with the exception of y, which I will be accessing by reference. Okay, so if you capture an object by value, that means that you want to have read-only access to that object within the body of your lambda. Whereas if you capture an object by reference, that means that you want to have both read and write access to that object. Now, it turns out that capturing only applies to local variables and parameter variables. Global variables or static local variables cannot be captured according to the standard. It does turn out that GNU C++ allows it, but that's not a portable feature. So you may discover that your compiler allows it in some cases, but you should not rely on that to be true. By the way, when you capture an object by value, the value that gets used for that particular object within the definition of the lambda is whatever value that object had at the moment where the lambda was defined. Okay, this is getting a little too hypothetical. Let's take a look at some examples to illustrate what's actually going on. Here on slide 11, we're using a couple of different capture notations, and on slide 12, we have the output resulting when we run this program on slide 11. Okay, so within main, we have a local int object named I, which is initialized with 4, and we have a local double object named x, which is initialized with 0.125. We're defining a lambda here that we're going to name lam1, and in this lambda, we're capturing all of the objects in scope by value. Now, the two objects that are in scope here are the local variable I and the local variable x. So we're capturing the current values of those objects for use in the body of the function. That is, if I use I in the body of the function, that will be replaced with a 4, and if I use x within the body of the function, that will be replaced with a 0.25. Okay, so when I call lam1 with the function call operator, what I get displayed is this black output. 4 is the value of I at the point where that lambda was defined. 0.125 is the value of x at the point where that lambda was defined.